Let's look at this idea of parametric coordinates. So what are they? Basically, it's just another way of describing relations, so graphs. Okay? We're used to using Cartesians. So a Cartesian form is when we describe the shape or the graph with one equation, so that's the graph, and then an individual point we describe with two numbers, the x and the y value. Parametric, meaning pair of measures, parametric, is the other way around. We describe the curve with two equations. So we have a pair of measures, and our points then are just described by one number. So if we wanted to get the actual coordinates of the number, we'd sub that same number into both of the two equations. And we come up with it. So look, let's just do the parabola, which of course we know Cartesian, y equals x squared. Now one way I could write the parametrics is like this. If I said x is t on 2 and y is t squared on 4. So I've got two equations representing that curve. One's telling me what the x values are doing, one's telling me what the y values are doing. So if I was to plot a point, minus 1, 1, well that's the Cartesian coordinates. The parameter for that is t equals negative 2. Because if I was to substitute it into the parametric equations, I would get minus 1, 1. So that's the parameter. Minus a half, a quarter would have a parameter of minus 1. The origin would still have a parameter for this one of 0. There's a half, a quarter, t equals 1, so we've still got that symmetry about it. And 1, 1 would have a parameter of 2. So it's just a different way of describing graphs. So how do we change from one form to the other? So if I want to change a parametric to Cartesians, and there's the fancy definition. So x is some function of t, y is some other function of t. They're the parametric equations of a curve. And all you need to do is eliminate the parameter. It's like simultaneous equations. You're eliminating the parameter. We want to get rid of the t and bring it all back into Cartesian coordinates. So if I'd got this one here, x is 2t plus 1, y is 3t minus 2. They're telling me this should be a straight line. Okay, well let's go show it. It doesn't matter which way around I go. I just need to make t the subject in one of these, substitute it into the other. So if I make t the subject of the x equation, I get that t is a half of x minus 1. Substitute it into the y equation and play around with it, and sure enough, that's something we recognise to be a straight line. Of course, we can get some really interesting ones. So you've got x equals 2 plus cos theta, y equals 1 plus sine theta. So the parameter here is theta. How do I get rid of theta? I mean, it's not just, well, make theta the subject. It's a bit hard. I mean, it can be done, but we're going to make use of, you remember this trig identity? You've seen that one? You know, sine squared plus cos. I'm going to make use of that. So rather than making the theta the subject in this, I'm going to say, well, I'll make cos theta the subject in the first one. I'll make sine theta the subject in the second one. And I'll substitute it into that relationship, which I know is always true. So sine squared theta plus cos squared theta, although I've actually gone cos squared plus sine squared, but that doesn't matter, is equal to 1. And we recognise that, hopefully, straight away. Oh, we've got a circle. Centre 2, 1, radius 1 unit. But then we can really get some good ones. So we're going to complete the table of values. The x parameter is sine theta. The y parameter is sine 2 theta. We're going to do it by plotting some points here. And so the angles I'm going to sub in are 0, 30, 60, 90 and so on up to 360. But to save some time, I've already done that table of values. And so let's plot them. Okay. We'll go there, then there, then there, down there, down there. Whoop. Still not 100% sure what it is, so I can always choose more points, but it ends up being that. Now the interesting one now is, let's find its Cartesian equation. Well, I know y is 2 sine theta cos theta. It's another one we'll see later on, but trust me, if you don't know that one, it's true. Sine 2 theta is 2 sine theta cos theta. Now, I know sine theta is x, but how do I get cos theta? Well, if I draw myself up a little triangle there, and I know that sine theta is x on 1, so opposite over hypotenuse, so the adjacent side must be the square root of 1 minus x squared, I can now substitute in for the sine theta and the cos theta, and there's y equals 2x square root of 1 minus x squared. But that's not good enough. I'm going to square it, right? Because remember how when we did the square root graph, we get top half, bottom half. That y equals 2x squared of 1 minus x squared would just be the first quadrant and the third quadrant. Because when I sub in a positive number into that, I'll get a positive. If I sub a negative number into that, I'll get a negative. So it'd only give me half the shape. So a bit like top half of a circle is the semicircle. Same idea. So if I square both sides, then I can get the complete shape we've got over there. Y squared is 4x squared. Tidy that up, and there's its equation. And if you don't believe me, plug that into Desmos, and you will see that that is, in fact, the butterfly shape that we've got there. Let's have a look at 5H to finish off this topic, and parametric coordinates.